Okay, let's look at another example of power series. Our last one, we ended up with an interval that was finite. Let's look at an extreme here where actually all x's are going to work. So as always, we start off with ratio or root. And remember, factorial tells us that ratio is the way to go because we don't know how to take the limit of the nth root of n factorial. So we'll set up our ratio test. Rho is the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial. That's our a sub n plus 1 over x to the n over n factorial. So we flip that. And we have x to the n plus 1 n factorial being multiplied up top, and x to the n times n plus 1 factorial on the bottom. And so we know that simplifies nicely. These are, remember, the hallmarks of a ratio test: exponents and factorials. The x's cancel, leaving just an x up top. And on bottom, we have n plus 1, but I'm going to drop the absolute value because n plus 1 can't be negative. It's a natural number plus 1. Now remember, the limit is of n, so absolute value of x is a constant. If you like, you could even write it on the outside of the limit. So we're really taking this, right? That's going to infinity. So this limit equals 0, no matter what that x is. If x is 5, times 0 is 0. If x is 100, times 0 is 0. If x is 0, times 0 is 0. So no matter what x is, that is less than 1 for all x. So what we've figured out then is our power series, and from 0 to infinity, x to the n over n factorial, converges absolutely for all x. Which is great because we're done, right? There's no endpoints to check because it's all real numbers. No matter what x you plug in there, you get a convergent series. And actually, this is going to be really nice for us later on. This is really exactly what you want from a power series, because where we're headed with all this is writing power series representations of functions. And so if this is going to represent a function, what we've just established is that no matter what x you'd like to evaluate the function at, you get a convergent series. So, and actually, that series right there turns out to be the series for the function e to the x. So it's going to turn out to be true for all x. So this is great. No endpoints to check. We're done. So if this limit comes out to be 0, essentially the part without the x, then it's less than 1 no matter what x is. And you have a power series that converges for all real numbers.